Welcome to part 6 of our epic Metroidvania tutorial series. Get ready for some thrilling additions to our game mechanics and level design. In this installment, we'll introduce a flying enemy and 2 ground enemies, adding intense battles that will put your skills to the test. To enhance the game's immersion, we'll implement a smooth camera system with camera bounds, ensuring seamless and visually pleasing movements. Of course, we can't forget the platforming challenges. We'll be incorporating spikes that will demand precision and timing from players. By the end of this tutorial, you should have something that looks like this. So according to YouTube statistics, only a small percentage of people who watch these videos are actually subscribed. So if you'll end up liking this video, consider liking and subscribing. It's free and you can always unsubscribe later. Without further ado, let's get started. First, I would like to fix a bug that was pointed out to us by this commenter. They pointed out that when the player dashes into an enemy, time is frozen and does not speed up again. Next, let's create some enemies for our Metroidvania. First, we'll create a folder in our art folder called enemies and 3 more folders inside our enemies folder called bat, charger, and crawler. These 3 I'll be using sprites from 3 different assets for our 3 enemies, and the link is in the description below for these assets. Add the dark monster sprites to the crawler sprites folder. Add the bat enemy sprites to the bat folder, and finally add the green monster sprites to the charger folder. These will be the sprites we'll be using for the aforementioned enemies. Let's go to our editor and change the zombie sprites to the dark monster sprites and rename the zombie as our crawler. Resize the crawler scale as you see fit. For me, I'll be making its scale 0.25. Next, adjust the box collider 2D size to fit within the crawler. Once that's done, let's go back into the crawler script. We'll delete the fixed update, and on collision state 2D functions, as well as the enemy gets hit method, as we won't be needing those for our crawler besides what the enemy base class already has.
No.
I can't believe you've done this.
Next, we'll go to our enemy script and we'll create an enum called enemy states and an enemy states variable called current enemy state. This enum will hold all of our enemy states within it. We'll then create 2 states for our crawler, one called crawler_idle and the other called crawler_flip. Next, create a protected virtual method called update enemy states and call it in the update function. In this method, we'll use a switch function to switch between the different enemy states. For now, let's leave this method blank. Finally, let's create a protected method called change states and pass an enemy states argument called _new state into the method. In change state, we'll then set the current enemy state as the new state. Next, let's go back to our crawler script and create a protected override update enemy state method. In this method, we'll use a switch statement to switch between our different states. In case crawler_idle, we'll make it so that the crawler simply walks to the right at a steady rate. To do this, we'll set the horizontal velocity of the crawler's rigid body to the speed variable by typing if transform.localscale.x is more than 0, rb.velocity equals new vector2 speed rb.velocity.y, else rb.velocity equals new vector2 minus speed rb.velocity.y. For flip, we'll want the crawler to wait for a period of time, then flip to face the opposite direction, and then switch back to its idle state. To do this, we'll create a float called timer and add time.delta time to it in the crawler flip case. Next, we'll create a serializable private float variable called flip wait time. In the crawler flip case, we'll check if the timer is more than flip wait time. If it is, then we'll reset. If it is, we'll reset the timer back to 0. Set the transform.localscale.x to be multiplied by -1 so our crawler flips, and change the crawler state back to the idle state. We need the crawler to flip when either it walks into a wall or reaches the end of the ground. So what we'll do is use a raycast to detect if the crawler detects a ledge or if it hits a wall. First, we'll do a ledge detection by creating a raycast that checks if there's a ledge. If the crawler encounters a ledge, it will wait for a moment before turning and flipping to the opposite direction. To do this, we'll need to create a few variables for our raycast. First, we'll need to create two more serializable floats called ledge check X and ledge check Y. Ledge check X will determine how far away the ledge check will be from the crawler, and ledge check Y will determine how far down the raycast ledge check will travel. Next, we'll create a serializable layer mask variable called whatisGround. Then, in update enemy states, we'll check if the crawler is facing the left or the right. If the crawler is facing the right, we'll check raycast downwards for a ground object. If there isn't one, then we flip the crawler. Then if the crawler is facing the left, we'll do the same raycast except with a negative ledge check X. Next, in our crawler idle state, we'll create two local variables, one vector3 variable to determine where the ledge check will start at, and another vector2 variable to determine the wall check direction. We'll set these two local variables by checking if the crawler's transform.localScale.x is more than 0. If it is, then the crawler is facing the right, and if it isn't, then the crawler is facing the left. Then we'll use the local variables in our raycast, and here's the implementation. Vector3 underscore ledge check start equals transform.localScale.x is more than 0, question mark, new vector3 ledge check x, comma 0, colon, new vector3 negative ledge check x 0. Vector2 underscore wall check dir equals transform.localScale.x is more than 0, question mark, transform.right, colon, negative transform.right. If not, physics2d.raycast transform.position plus underscore ledge check start, vector2 down, ledge check y, whatisGround, or physics2d.raycast transform.position underscore wall check dir, ledge check x, whatisGround. Then change state, enemy states.crawler underscore flip. Let's then add the ledge check code to the idle state case, as the crawler doesn't need to check for a ledge in the flipping state. Let's finally create an animation for our crawler with the two dark monster sprites. Make sure the animation is looped. Then head back to the inspector and set the crawler's health to 3, damage to 1, speed to 5, recoil length and effector to 0, flip wait time to 1, ledge check x to 1.2, and ledge check y to 1. Now if we test the crawler in our editor, we should have an enemy that patrols on the top of a platform without falling off, and also pauses before it turns to the opposite direction. Set whatisGround to ground, and finally set orange blood to the orange blood particle system. Now if we test the crawler, we should have a crawler that moves back and forth on a platform without falling off. Next, we'll create the bat enemy. This enemy will stay in the air until the player gets close enough to it. It will then start chasing the player. Let's first create a game object using one of the bat idle sprites as the sprites for it. As with the crawler, you can resize it however you see fit, and as for me, I'll be scaling it to 0.6. Next, we'll add a circle collider 2D and resize it to fit inside the bat. Then add a rigid body 2D and set the rigid body 2D's gravity scale to 0, as our flying enemy won't be affected by gravity. Then set collision detection to continuous and interpolate to interpolate so we won't run into collision detection issues. Freeze the Z rotation of the rigid body 2D and we should be good to go. Create a script called bat and have it inherit from the enemy class. For our bat, I have 5 states to add. First, the idle state in which our bat will stay still, a chase state where the bat will chase the player, Then we'll have a hurt state in which the bat will be in hit stun and knocked away from the player. And finally, we'll have a death state where the bat's death animation plays and the bat gets destroyed with an orange particle system. We'll add these 5 states into our enemy base class as bat_idle, bat_chase, bat_stunned, and bat_death. Delete the update function of our bat script, and in the start function, we'll make sure the base.start is called, then set the current enemy state to bat_idle. Then add a protected override void update enemy states, and add a switch statement with cases for each state for the bat. For the bat idle state, we'll need to make it so that the bat will change to a chase state when the player is near it. To do this, what we'll do is detect whether the player is in range of the bat. We'll create a serializable private float variable called chase distance, which will be the distance at which the bat becomes aggressive to the player. Create a local float variable to keep track of the distance between the bat and the player, then check if the value is less than the chase distance. If the if statement is true, then change the bat state to bat chase. Next, for the bat chase, we want the bat to move towards the player smoothly, so what we'll do is use vector to move towards to move the bat's position towards the player's position, and use time.delta_time multiplied by speed for the step value. We'll then use rb.movePosition to move the bat position using vector2.moveTowards. We'll want the bat to look towards the player when in the aggro state, so we'll create a method called flipBat. Then we'll create a variable to reference the enemy sprite renderer called sr in our enemy script. Then set sr.flipx to true when the player's x position is lesser than the bat's x position, else set flipx to false. Let's also improve the recoil for our enemies. First, go to our enemy script and make _hit force positive and set it to rb.velocity rather than using rb.addForce. Next, go to our player controller script and instead of using the direction from the player to the enemy as the recoil direction, we'll instead change the ref_bool parameter to _recoilBool and pass in a new vector2 argument called _recoildir. Then, set the recoildir argument to the direction that the player is hitting in. The down slash will be vector2.down, the up slash will be vector2.up, and for the side attacks, we'll create a local variable called _recoil left or right and use a ternary operator to set it to 1 if the p_state.lookingright is true and to -1 if the p_state.lookingright is false. Then we'll hit to our enemy script and move the update enemy states to an else statement under if is recoiling. Next, create a float timer variable and add time.delta_time to it while in bat stunned. Create a serializable private float called stun duration, then in bat stun state, when the timer is more than the stun duration, change states back to bat idle and reset the timer to 0. Finally, for bat death state, remove the destroy game object state if health equals 0 from the enemy script, and then go to our crawler script and destroy game object if health equals 0 in the update enemy states method. Then in bat script, create a protected override void of the enemy gets hit method while calling the base method, and if health is more than 0, change states to bat stunned, else change states to bat death. Let's now create the orange particle explosion for when an enemy gets hit. First, go to the hierarchy and right-click effects, particle system. Next, modify the settings, change the duration to 0.1, set looping to false, set start lifetime to random between two constants 3 and 5, set start speed to 10, set start size to random between two constants 0.1 and 0.75, set the gravity modifier to be a curve that dips below 0 at the start then goes back up. Then go to emission and change the rate over time to 200. Next, change the shape to a circle. If your particle system doesn't look like a circle, make sure to reset the transform. Change the linear x value to 1, the y value to 5, and the z value to 0. Change the speed modifier to a curve that looks like half of a quadratic graph. Next, enable collision and set the type to world. Set mode to 2D, set dampen to 0.1, set bounce to a random between two constants 0.1 and 0.5. Then set particle speed and size to true and set collides with only to the ground layer. Next, enable texture sheet animation and change the mode to sprites, then set the sprites to a circle sprite from the packages folder in your project tab. Next, go to enable trails, set lifetime to a random between two constants 0.03 and 0.05, set width over trail to a curve, and set the endpoint to 0. Finally, set the renderer's sorting layer ID to midground and set the order to the same as the player's. Make this a prefab. Then in our enemy script, we'll instantiate the orange blood so that it instantiates whenever an enemy gets hit. First, get a reference to the orange blood in the enemy script by creating a serializable private GameObject variable called orange blood. Then we'll create a local GameObject variable for the orange blood and set it to an instantiated orange blood at the enemy's transform.position and quaternion.identity. Finally, destroy the orange blood particle system we instantiated in 5.5 f-seconds. Let's also make sure our particle has time to instantiate by creating a protected virtual void death method in our enemy script while passing in a float argument called _destroy_time, then setting the game object to destroy in destroy time in the method, stunned and bad death, with an underscore as the spacing. We'll then make sure that bad_stunned and bad_death animations aren't looped, since we only want them to play once. Now what we'll do is go to our enemy base class and create a protected virtual enemy states property called getEnemyStateChange. This will help us detect whenever the state of the enemy has changed. First, we'll get the current enemy state variable by returning it. Then, if current enemy state is not equal to the value of getEnemyStateChange, we'll set the current enemy state as the value. Then change all of the current enemy state variables we use in all of our enemy scripts to the getCurrentEnemyState property. Next, create a protected virtual void called changeCurrentAnimation and call it in currentEnemyState is not value if statement. What this does is allows us to call for a change of animation parameters whenever the enemy state is changed. Now create an animator variable called anim and get a reference to the enemy's animator in our enemy script start function. Now head back to the bat script and create a protected override void of the change enemy animation for our bat animations. Go back to the editor and go to the animator tab for our bat. First, create 3 bool parameters called idle, chase, and stunned, and a trigger parameter called death. We'll then transition from our bat idle state to the bat chase state when chase is true, and then we'll transition from bat idle to bat chase when idle is true. For our bat stunned and bat death states, we'll transition to both of them from any state. When the stunned bool is true, or the death trigger is triggered respectively. For all these transitions, we'll want to have no exit time as well as no transition duration, as we need to make sure that these transitions happen instantaneously. Next, we'll transition from bat stunned to bat idle, when idle is true and stunned is false. Then we'll transition from bat stunned to bat chase when chase is true and stunned is false. For these two transitions, we don't want transition duration, but we do want exit time, as we want to make sure that the stunned animation is complete before transitioning out. Let's go back to our bat enemy script and add to the change enemy animation method. We'll set the idle bool parameter to the bool value of the getCurrentEnemyState is equal to enemyStates.batIdle. We'll do the same for the chase and stunned bool parameters by setting their truth value to if the current enemy state is equal to their corresponding enemy state. Finally, set the death parameter to trigger if getCurrentEnemyState is equal to batDeathState. Lastly, for our batDeathState, we'll call the death method and pass in a random.range between 5 and 10 as an argument. Then we'll create a protected override void death and set the bets. Set the bet. Then we'll create a protected override void death and set the bed's RB.gravity scale to 12 before calling the base death method. This is so that we can have the corpse of the bed before it gets destroyed. So all we'll have to do is go into our enemy scripts on collision enter 2D function and add a health is more than 0 check to the if statement. Go to the editor and set the variables. For me, I'll set health to 5, damage to 1, speed to 12, recoil length to 0.5, recoil effector to 0.3, chase distance to 15, stun duration to 5. Remember to also set the orange blood particle system. Now if we test our game, we should have a working bed enemy that chases the player around. Next, let's make the charger enemy. The charger will charge the player when the player is in line of sight and stop when the player is not. First, we'll duplicate the crawler in the editor, rename the duplicate to charger, and replace the sprite with one of the charger sprites, then resize the box collider 2D to fit within the charger sprite. Next, remove the crawler script from our charger and create a new charger script that inherits from the enemy base class. Next, we'll create 3 stages for our charger in the enemy script: charger underscore idle, charger underscore surprised, and charger underscore charge. Next, copy the crawler script and paste it into the charger script. We'll do this as the charger and crawler's idle states are basically the same, with the difference that the charger won't change to a flip state but instead just flip immediately, so just replace the change state to the line of code that flips the charger and then delete the crawler underscore flip state. Make sure to then replace all of the crawler states with the charger states. Let's also remove the flip wait time as we won't be using it. Next, create 2 serializable private float variables called charge speed multiplier and jump force. Then create a charger underscore surprised case. In it, we'll set the rb.velocity to new vector 2, 0, jump force. This makes it so that the charger will jump upon noticing the player. This is the feedback that tells the player that the charger has noticed them and gives the player time to act against the charger's charge. Then create a local raycast hit 2D underscore hits variable and set it to physics2d.raycast transform.position plus let's check at start underscore wall check dir let's check x times 10 if underscore hit.collider is not null and underscore hit.collider.gameObject.compare tag player, then change state to charger underscore charge state. In the charger underscore charge state, we'll add time.delta-time to timer. Then add an if timer is less than charge duration statement. Then a if physics2d.raycast transform.position vector2.down let's check y, what is ground inside of it. Then finally with the idle movement code inside of that if statement, but with the speed multiplied by the charge speed multiplier. Else if the raycast fails and the charger isn't on the ground, we'll set the rb.velocity as new vector 2, 0, rb.velocity.y so that the horizontal velocity of the charger is stopped when it is in the air. Finally, add an else statement to the timer is less than charge duration if statement and reset the timer back to 0. Then change state back to charger underscore idle. Finally, for our protector override change enemy animation method, all we'll do is set nm.speed to 1 when get current enemy state is charger underscore idle, and the nm.speed to int charge speed multiplier when the get current enemy state is charger underscore charge. Now if we set the charger's health to 10, damage to 1, speed to 3, recoil length to 0.1, recoil factor to 0.75, orange blood to orange blood particle system, charge speed multiplier and charge duration to 3, jump force to 20, let's check X to 1.2, let's check Y to 1, and what is ground to ground. And test the charger out. We should have an enemy that gets surprised and charges the player when it sees the player. Next, we'll be making spikes as our platforming challenge. We'll first download the 2D obstacles collection that is linked in the description. Then we'll set a respawn point. Create a public vector2 variable called respawn point in the game manager script. Then create a physics sprite shape by right-clicking the hierarchy and selecting 2D objects, physics, sprite shape, but remove the sprite renderer. Create a script called respawn point and add a onTriggerEnter2D. In the onTriggerEnter function, if _other has the player tag, then set GameManager.instance.platforming respawn point to transform.position of the respawn point. Then we'll create a physics sprite shape by right-clicking the hierarchy and selecting 2D objects, physics, then sprite shape. Once done, change the sprite to spikes_2sprite, set the order to -1 and reset the transform. Set the box collider to isTrigger. Let's then create a new tag called death and set the spikes to death. Next, create a script called spikes. We'll create an onTriggerEnter2D function and check if the _other has the player tag. Next, we'll create a coroutine called respawn@platform. In it, we'll type player.instance.pState.cutscene is true, player.instance.pState.invincible equals true, player.instance.rb.velocity equals vector2.0, time.timescale equals 0, start coroutine uimanager.instance.scenefader.fade, scenefader.fade direction in, player.instance.takedamage1, yield return new, wait for seconds 1, player.instance.transform.position equals GameManager.instance.platforming respawn point. Start coroutine ui.instance.scenefader.fade, scenefader.fade direction.out. Yield return new, wait for seconds uimanager.instance.scenefader.imagefade time. Player.instance.pState.cutscene is false. Player.instance.pState.invincible is false. Finally, time.timescale equals 1. Let's then call it in our onTriggerEnter2D function if statement. We'll want to set our platforming respawn points at different points in the scene, like near the hazards that you've set, and near scene entrances so that the respawn points function gets set when the player enters the scene. Make our spikes and enemies into prefabs. I'll be spreading these hazards around the cave scenes so that there are some challenges in the levels. For example, I'll be adding spikes under the platforming section of cave_2 and respawn points that are right on top of the scene entrances that have platforming hazards near them. This is so that a sort of default respawn point is set immediately when the player enters the scene. Let's finally imitate Hollow Knight's perspective camera. We can first remove the camera follow script from our camera, as that camera is very basic and we won't be able to replicate the mechanics of Hollow Knight's camera with it. Let's then install the Cinemachine package from the Unity registry in the package manager. Next, add a 2D Cinemachine camera by right-clicking the hierarchy and selecting Cinemachine, 2D camera. This will create a virtual camera with the Cinemachine virtual camera component on it. Name this virtual camera Open Room Camera, then set the Cinemachine body settings to Tracked X to 1, Look Ahead Time to 0, Look Ahead Smoothing to 1, Look Ahead Ignore Y to True, X Damping to 0.75, Y Damping to 2, Z Damping to 0, Soft Zone Width to 0.2, and Height to 0.35. Let's then change our flip code to something rotation based by flipping the player's y-axis to 180 degrees when looking to the left. This is done so that the tracked offset of our cinemachine will flip as well when the player flips. Let's then create a parent game object for our camera related game objects called cameras. Make this a prefab and add prefabs to the other scenes. Now let's add camera bounds. Go to our open room camera and go to the cinemachine brain component. From there, go to add extensions and add a cinemachine confiner 2D component. Then create another empty game object called open room camera bounds and add a box collider to it. Expand the box collider to the edges of the parts of the scene you want invisible. Then check used by composites and add a composite collider to the top of the box collider. Set the composite collider to is trigger so that it doesn't affect collision in gameplay. Note that you can use a polygon collider instead of a box collider to shape your camera bounds. I don't recommend it, however, as polygon colliders can cause weird camera movement if not set up in a very precise manner. Instead, what I like to do for rooms that have a different shape to them is to use a composite collider to combine multiple box colliders. All you have to do is make sure that the box colliders have their used by composite checked and have the composite collider be at the top, as the cinemachine confiner takes the first collider it detects as an object. Notice how I've sealed off the room on the right of cave 3 and I've excluded it from the camera bounds. This is due to the fact that I want this room to be a sort of secret room and I want it to have its own camera bounds. To do so, we need to be able to swap between different cameras and have different camera bounds. Let's duplicate our open room camera and call this copy secret room camera. Let's also create secret room camera bounds and assign it to the secret room camera confiner. Once this is done, we'll create a script called camera manager and add public static camera manager instance private void awake. If instance is null, instance is this. This is so that we can get a static reference to the camera manager in every scene without having to make it a singleton. Next, create a serialized field array called all virtual cameras of type cinemachine virtual camera. This array will hold all of the references to all the virtual cameras in our scene. Then declare a private variable called current camera of type cinemachine virtual camera. This variable will keep track of all the currently active cameras in our script. Add for int I equals 0, I is less than all virtual cameras.length, I++. If all virtual cameras I.enabled, current camera equals all virtual cameras I. Framing transposer equals current camera.get cinemachine component cinemachine framing transposer. This is done to check each camera's enabled property to find the currently active camera. We then assign the found camera to current camera variable. Add for int I is less than virtual cameras.length, I++, all virtual cameras I.follow equals player.instance.transform to start. This, for each camera of type cinemachine virtual camera in the array, sets its follow property to the player. Then add public void swap camera cinemachine virtual camera underscore new cam. Current camera.enabled equals false, current camera equals underscore new cam, current camera.enabled equals true. To call the swap camera function, we'll add a script called camera trigger to your secret room camera bounds. In the script, add a serializable private cinemachine virtual camera called new camera and set it in the inspector to the camera that the camera bounds is being used by. Then add private void on trigger enter 2D collider underscore other. If underscore other.compare tag player, camera manager.instance.swap camera new cam. This calls the swap camera function when you enter a new camera bounds area. By attaching the script to all of our camera bounds and assigning the new camera variable, we smoothly transition between cameras. Now let's test this out. The transition looks smooth. However, it seems a little slow for my taste, so I'll increase the transition speed by going to our cinemachine brain on our main camera and changing the swap time to 1 second. And voila, a smooth camera transition. Finally, let's also increase and decrease our white damping so that the player will be able to see below them when they are falling. To do so, let's go back to our camera manager script and add header, white damping settings for player jump/fall, serialized field private float pan amount equals 0.1f, serialized field private float pan time equals 0.2f, public float player fall speed threshold equals -10, space 5, private float normal white damp, public bool is lerping white damp, public bool has lerped white damping, private cinemachine framing Next, add normal white damp equals framing transposer dot m underscore white damping to the bottom of the awake function. Next, add a public enumerator called lerp white damping with a bool underscore is player falling parameter. In the coroutine, add is lerping white damping is true, float underscore start white damp equals framing transposer dot m underscore white damping, float underscore n white damp equals 0, then if underscore is player falling underscore n white damp equals pan amount has lerped white damping equals true, else underscore n white damp equals normal white damp, float underscore timer equals 0, while underscore timer is less than pan time, underscore timer plus equals time dot 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 time, float underscore lerped pan amount equals mathf.lerp underscore start white damp underscore n white damp underscore timer divided by pan time, framing transposer dot m underscore white damping equals underscore lerped pan amount, and you return null. Is lerping white damping equals false. This gradually adjusts the m underscore white damping property of a cinemachine framing transposer component to create a smooth transition effect. To call this coroutine, we'll add a method called update camera white damp for player fall to our player controller script. In it, we'll add if rb.velocity.y is less than player fall speed threshold and not camera manager.instance.is lerping white damping and not camera manager.instance.has lerped white damping, start coroutine camera manager.instance.lerp white damping to true. If rb.velocity.y more than or equal to 0 and not camera manager.instance.is lerping white damping and camera manager.instance.has lerped white damping, camera manager.instance has lerped white damping is false, start coroutine camera manager.instance.lerp white damping false. This method checks the player's vertical velocity and triggers certain camera behaviors based on the velocity conditions. The first if statement checks if the player's vertical velocity is below a certain speed threshold to see if the player is falling fast enough. It also checks if the camera is not currently lerping the white damping and if the white damping has not already been lerped. If the conditions are met, we call the lerp white damping coroutine and set underscore is player falling to true. The second if statement checks if the player is standing still or moving upwards. It also checks if the camera is not currently lerping the white damping and if the white damping has already been lerped. We then call lerp white damping coroutine, but this time setting underscore is player falling to false. And with that, part 6 has come to a close. In the next part, my partner Matias will cover how you can create a simple save system using binary writer as well as the player death mechanic. He'll be introducing a simple updating map UI akin to something you would find in Metroidvanias like Hollow Knight or Metroid. Hey there! Want to support what we do? You can help us by becoming a patron. This will give you access to the project files for our tutorials as well as Patreon exclusive posts on our blog. Any support you give will be invaluable to us, as currently we're only making back about 20 cents for every dollar we put into content creation. Your patronage will go a long way to help us make this a sustainable endeavor. See you in the next video!